Okay. We're going to do top hat a little later to reward you for coming. Thank you. Okay, so let's start off with one more example of the analyzing covariation increment by increment. I know it's a little tedious, but we want to practice it and especially review again that difficult situation of when that quantity is decreasing. It's confusing, so we want to do that again. So I'm going to kind of look a little bit silly here. But, all right, so what we're going to do is, so the Constitution's on the wall over there. And so we're going to look at two quantities. What's going on? There we go. Okay, so we're going to look at two quantities. Time since I started walking and my distance from the Constitution. So which one of those is independent? So the time since I started walking, that's a quantity. My distance from the Constitution. Are these constant quantities or changing quantities? Remember our first week of class, right? We talked all about so, and the whole point of the class is covariation, how two changing quantities change together. And so we're analyzing this without formulas, right? With all relative sizes, no numbers, no formulas. Okay, so what would be natural to put as my independent quantity on the x-axis? Yeah, the time since I started walking. And then my distance from the Constitution on the wall over there as the kind of the focal quantity that we're asking about the rate of change of. Okay, so do this right. So okay, I'm gonna do this what's called a walk a couple times, so you have to kind of memorize what my behavior is, and then we're going to apply it when you have that image in your mind, and we'll break it down little by little. Okay, so. Ready? So time is going to start right now. What is he doing? Right? Okay, so I'll do it again. So you got to just kind of remember what I did, and then we'll create the graph. Okay. We're grown man. Ready? Time starts now. Okay. So, was I consistent both times? Was it the same thing both times? Cool. All right. So, if we want to start this, we want to start at time 0. So, time 0. My distance is 0. Right? Time 0. So I'm going to start the graph here like the bottle problems, right? No, right? Because now at time 0, my distance was not 0. So I had some positive distance. So does that mean I'm over here like this? So something like this. So now how is my distance represented in this graph at the start, before I started walking? How is the distance represented? Yeah, but how is it represented on the graph? Isn't it this distance right there? So that from there to there, whatever that interval segment length is, that's how far away I'm starting from the Constitution. Okay, so in the first little bit of time, what did my distance do? Did it increase or decrease? My distance from the Constitution, did it increase or decrease? Did it increase a lot or a little? Started off with a big step, right? So that gives us a point. Next little increment of time. What did my distance from the Constitution do? Increase or decrease? Increase. Now that change, that amount of increase, was it more or less than the previous? A little bit less, right? I took a smaller step. Next increment of time. My distance increased or decreased? Increased. The amount of increase, more or less than the previous increase? A little bit less. So with each passing increment of time, my distance is increasing, but the changes in distance are getting smaller, decreasing. Until finally, I hit some maximum distance away. I was over at that wall over there. Okay, so I'll draw the actual graph in black so we can connect the dots. So with each change in distance, it gives us a point on the graph like this. Constant rate of change? No. So is the rate of change then increasing or decreasing?
Increasing or decreasing?
No, the rate of, I'm just asking about the rate of change. I'm not crazy about those phrases where you try to put it all together at once. Answer two separate questions. It's less confusing. So the distance itself, is it increasing or decreasing? Increasing. The rate of change is decreasing. The rate of change is decreasing, and that's seen by the changes. If the changes are decreasing for the same increment of time, if I'm covering less and less distance with each increment of time, then my rate of change is decreasing. Okay? We good so far? That's the easy part. All right, so then in the next increment of time, did my distance increase or decrease? Decrease. A lot or a little? Remember how I started over there? I took a big step, right? I took a big step. So now we have a change in distance. Is that change in distance positive or negative? We want to distinguish between increasing and decreasing by labeling our changes either positive or negative. If I get further, if distance increases, that we call that a positive change. If the distance decreases, which it did here, we want that to be a negative change. Okay, so we have a negative change in distance. Next increment of time. What did my distance do? Increase or decrease? Decrease. So the change in distance is positive or negative? Negative, okay. Next change in distance is negative. Was that change more negative or less negative than the previous? More negative or less negative? Did I take a smaller step or a bigger step? My biggest step was at first, right? Or my greatest speed was at first. And then? Yeah, so less negative of a change. Do you see that? Less negative of a change. Okay, next increment. My distance decreased or increased? Decreased. That change then is negative. Then that one, more negative or less negative? Still less negative. Okay, that's this one. So what's happening? The changes are becoming less negative or more negative? Less negative. Okay, so for instance, this one's say this one's -8. That change was -8, whatever unit we're talking about. And then this one was -6. And then this one's -5. So that's the progression of changes. I'm just pulling those numbers out of a hat. But that's the idea, that the changes are becoming less negative. So if those changes are becoming less negative, are those changes increasing in size or decreasing? Are they increasing in size or decreasing? This is what's confusing. That's an increasing sequence of values. You see? What about the magnitude of those changes? The magnitude, they're getting shorter, but because they're negative changes and they're getting less negative, to be consistent, that's increasing changes. Okay, and that continued on until maybe a couple more increments here. And then I got to the middle again, and in the next increment of time, did my distance increase or decrease? It continued to decrease, more or less than the previous. More of a negative change. Okay, and then with the next increment, more negative, right? Because what was I doing now? So I was speeding up. That's true. I was speeding up. So each change was more negative than the one before. So these changes, positive or negative? So maybe this is D6 or something. They're still negative changes. Are these changes becoming more negative or less negative? These changes are becoming more negative. More negative. So a sequence of values that become more negative, is that an increasing sequence or a decreasing sequence? Decreasing. So let's draw that. So if I connect the dots here, so that's kind of what it looked like on my journey back towards the Constitution. And then, from there, oh boy, lost control. You get the idea. Okay, so let's talk about, so here, the changes are increasing or decreasing? The changes are decreasing, so the rate of change is decreasing. It's easy when the function is increasing. It's just what you think, right? There's no kind of conflict. When the quantity is getting larger, if those changes get smaller, then the rate of change is decreasing. Okay? Now here, our changes, we're doing what? Yeah, so the change is increasing or decreasing? We want to see that as those changes increasing because they're becoming less negative. We want to see that as increasing changes because they're less negative. So the rate of change is? Increasing. And then finally, the changes here are negative and becoming more negative. So the rate of change is decreasing again. Okay, so the reason that we fight for this is so that there's consistency with the shape of the graph. If the rate of change is decreasing, notice what the shape of the graph is. What do we call that? Concave down. Cupped down. Concave down. Okay? Notice over here. We said the rate of change is decreasing, and it is concave down. So for these two, and it's consistent. If the rate of change is decreasing, it's concave down. Concave down, like a concave down, like a concave down, like a frown. Concave down, like a frown. I'm just here to teach you. Okay? And then rate of change is increasing, means it looks like concave up, like a cup. Yeah, yeah, like a smiley face too, but doesn't rhyme. So concave down like a frown, and that's the rate of change is decreasing. Whether it's becoming, the rate of change is becoming less positive or more negative, right? Less positive here, more negative. That's all a decreasing rate. Here, concave up, always rate of change is increasing, whether it is becoming what? Less negative or more positive. That's an increasing rate of change. Okay. Any questions on that? Yeah.
Would it be in terms of thinking of decreasing and increasing? Would it be wrong to think of it in terms of like a frequency? As it's going up, it's becoming I'm looking at like a.
Look at the changes. Focus on the changes. That's what we're doing. So focus on what's happening to the changes. First of all, are the changes positive or negative? And then, are they becoming more or less positive or negative? Focus on the changes, these vertical, the magnitude of these changes, along with whether it's positive or negative. That's what we're focusing on. Other questions? Okay. Can I erase? So, one type of function that has this kind of look to it, these rolling hills, right? These rolling hills where we're, increasing, concave up, concave down, is called a polynomial. Okay, so here's what a polynomial is. It's the sum of monomials with whole number exponents and real coefficients. Okay, so let's break that down. So a monomial is one of these things. That's a monomial. That's a monomial. Each of those is a monomial. Okay? So there's two parts to this. There's the power of x and the coefficient. So the power of x has to be, like I said, a whole number. So 0, 1, 2, 3, 4. Can't be negative, can't be a fraction, can't be a decimal. Got to be a whole number in order for it to be a polynomial. And then the coefficient is this multiplier out in front. That could be any real number, a decimal, a fraction, pi, a negative, doesn't matter. So that's how that definition works. So let's compare, say, just a monomial. Say this monomial, 10.5 x squared. Is that exponential growth? 10.5 x squared. Is it exponential growth? How do you know? Okay, so he's referring to our general form of an exponential function, which is a times b to the x. Is that what it is? Got a match there? People are nodding. What's the input? What's the role of the input in an exponential function? Which one of those is the input? What does it tell us? How many times to multiply together? What? What does b is? Oh, 4 weeks. The growth factor. Remember? The key element. So the input is telling us how many times do we multiply by the growth factor? How about in a monomial? It's the input. Is it the exponent? Oh no, it's the base, right? It's the base of that term. Are monomials exponential functions? Oh no, 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 no. So people are still saying yes. Here in exponential growth, the input is the exponent. It's telling us how many times we multiply the growth factor together, right? If x is 10, it's like the initial amount multiply by the growth factor 10 times to get the amount 10 times 10 units later. It's totally different here. Now the input is the base, okay? Totally different kind of covariation if you put the input in the base or the exponent. Okay, so just because it has a power, it doesn't mean it's an exponential function. An exponential function has the input as the exponent, telling us how many times to multiply that growth factor together. Okay, so monomials are not exponential growth. Monomials sum together give us a polynomial. Okay, and then some polynomials can be factored. This is two different functions, right? So here's an example of a polynomial in the expanded form, and this is one in the what's called the factored form. So today we're just going to focus on expanded form and what it helps us with in terms of representing the covariation, or in other words, graphing it. So if we wanted to graph this, to have a representation of how x and the output are covarying together, we would sketch a graph. And so what is it that we can get? What's one real fast, simple thing we can find out about this function looking at that expanded form? So real, just right off the bat, we can get.
You can tell how many groups.
Maybe we're not gonna go there. Even the slope is always changing in a polynomial. Changing rate of change. What's that? Y-intercept. What is a y-intercept? What is it? What characterizes a y-intercept? What do you know about a y-intercept? Okay, so suppose it's right there. What's always true about that? What do you know? X is 0 or y is 0?
X is 0.
Okay, students get real confused with this. A y-intercept does not mean that y is 0. It means that x is 0. It means we're not going to the right or left, but we do have some y value that we're going to go up or down. Okay, so if we're on the y-axis, the y-intercept, we're intercepting the y-axis, that's where x is 0. We don't go left or right. So, to find the y-intercept, if it's where x is 0, what do? Plug in 0 for x. So, we're looking at f of 0. But we don't even really need to do that, because what happens when f is 0? What do we get? Yeah, any term that has an x in it just goes away, and so we can focus on our constant term here. We don't really even have to plug the x in. We just look for the constant term because we know all the other terms will be 0 when we plug x equals 0 into it. So right off the bat, we can get the y-intercept. And that gives us this place, just what it says, where the graph intercepts the y-axis. Where it intercepts the y-axis. So for this f of x below, that'd be negative 3/7 right there. Okay, there's something else that the expanded form helps us with. Okay, and so we're going to spend the rest of the time in class today on. So y-intercept, quick, easy, but the trade-off is it's not much, right? It's all it is 1 point. So we know these graphs, or I'm telling you, these graphs are rolling hills with changing concavity and changing, increasing, and decreasing. So because it comes easy, it's not much. It's just 1 point. So we wouldn't know anything else about the rest of the graph except for that 1 point. Okay. All right. So the other thing we want to talk about is what's called end behavior. So I've got a bunch of terms down here that we're eventually going to talk about. But we're going to focus on this one, end behavior. Okay, so end behavior is associated with what's called the leading term. So let's see how that works. So if I'm going to make a new function here, h of x equals negative 7x cubed plus 4.3 x squared minus e. We know what that number is, right? EX plus 102. What's the y-intercept of h? What's the y-intercept of h? Where does it cross the y-axis? What's the x value there? 0. The x value is 0, and we get a y value of 102. Okay, so the leading term. So let's talk about that in a second. So end behavior refers to the nature of the graph at the ends. At the right end and the left end. So at the right end, so if we think about a graph here, we want to go way, way out to the right. What kind of x values do we have? Way, way out to the right. Big, are they positive or negative? So we call that x going to infinity. Or x increasing without bound. That signifies the far, far right end of our graph. And then the left end, x, decrease. So we call it, say, decreases without bound. Decreases without bound, and that puts us way, way out the left end. So this notation right here just means go way, way, way to the right on the graph, and way, way, way out to the left. And then we want to analyze what's happening. So let's pick, so going way, way out to the right kind of means like picking a really big number. So I'm going to pick 17 million, trillion. Okay, is that 17 trillion? No, actually that's 17 billion. Now it's trillion. Some of you know why I picked that number. Yeah. We in bad shape. Right? We in trouble. Okay. But we just live our lives like nothing's wrong. Okay. So here, notice, so if I pick this very, very large x value, which is kind of representing the right end, okay, I'm going to plug that in. I'm going to plug that value in everywhere there's an x, right? So let's just compare these first two right here. If I put 17 trillion into that, what does x cubed tell me to do with the 17 trillion? Cube it, which means? Yeah, what does it mean? What does it mean? So, Ryan said, multiply it by itself 3 times, right? And so x squared means multiply it by itself twice. So, how do these two, forget about the negative 7, just look at the x cubed and the x squared. How do those two terms compare? So which one's bigger, this one or this one? X cubed is bigger. How much bigger will x cubed be than x squared if x is 17 trillion? How much? Well, so this is 17 trillion multiplied together how many times? 3. 2. So how many times greater is this than this? 17 trillion. It's got one more 17 trillion. So next to this, even though you're multiplying together 17 trillion twice, next to this, it looks like what value? It's 17 trillion times as small. And we're not even really getting to large x yet. Okay? How about 100 zeros? How about 1,000 zeros? Okay? So this, no matter how big of a number you pick, this one will be that many times greater than this one. Do you see it? And so therefore, as x gets very big, this becomes like 0. It goes away. And this one certainly does. And 102 is nothing. Relative to this, because this is 17 trillion times greater. But now make it, 17 trillion to the 17 trillion. Make it an astronomically much bigger number. That's always going to be that number times greater than this. So that get the rest of terms, just pretend it's like 0 compared to that. So to analyze end behavior, we look at what's called the leading term. The leading term is the one with the highest power of x, because it will govern for these very, very large values of x. All the other ones just kind of fade away into the shadows because of how much bigger that leading term is.
So that's what end behavior is as x goes to infinity?
Yeah, end behavior is the ends, right? The right end is, this means let x be very, very large. The right end of the graph. The left end of the graph is x very, very large negative. Okay? So if we want to know the end behavior of this, what we're asking is, for h, as x goes to infinity, so that's over here, or as x increases without bound, what will h do? Well, h will do whatever the leading term does, because the other terms are virtually 0 when x gets big. So what will this do, the leading term, when x gets very large? So break it down. What will x cubed be? Will it be very large positive or negative? Just x cubed. Very large positive. And then we'll take that positive and do what? Multiply it by negative. So y will go to very large positive or negative? Negative. So what does that look like? As we go way out to the right, the graph will go down. That's the right end behavior for this negative 7x cubed. Because a large x cubed will be positive, but then we'll multiply it by negative. Okay, what about very, very large over here is our x going to negative infinity? Okay, so a very, very large negative x will be what? Will that x cubed, will that be very large positive or negative? X cubed. Very large negative. Because if it's an odd exponent, we're going to end up multiplying by an odd number of negatives, right? But then that negative will be multiplied by negative 7. So the whole leading term will be a very large positive. So y, as x approaches negative infinity, y will go to positive infinity. So as we go way out to the left, the y value will increase positive. So we're not analyzing the middle. We don't care about this. We just want the ends, the right end and the left end. So that's large x positive, large x negative, and the question we're answering is, what does the y value do when we do that? So this would be the end behavior for this h function right here. So strategy is identify the leading term, and then you look at x becoming very large positive and see what the leading term does. Does it become very large positive or negative? That will determine if it's going to go up or down on the right end. And then you look at x very large negative, and you see what the leading term will do. And that whatever the leading term does will determine if it goes, the h, or their function, goes up or down at the left end. Anybody have a question? Does that kind of make sense? All right, so try some practice in the book. Can I erase what I got up there?
You said the third step is, and then see what the leading term is when multiplied by the coefficient.
Yeah, so you're going to take your large value of x and put it into the leading term, and your goal is to find out if you'll get a large negative or a large positive in the end. So on page, I think is it 208? Is that 208? Yeah, I think it's 208, number 5. Do I have the right page number?
Yeah.
Thank you. So, first step, figure out what the leading term is. And then you Answer 2 questions. The end behavior. The end behavior. So for this function f, you're determining what is the graph like far out at the right end, far out at the left end. Okay, I'll make one round if you want to catch me for a question. The only thing it's about is y values increase positive or decrease negative on the way down the axis. Okay, what's the leading term for the first one? 5x to the third. You're looking for, is it always the first term? No, you're looking for the highest power of x. Okay? So, we're thinking of a very large positive number for x. What about x cubed? Positive or negative? X cubed will be positive times positive 5 gives us positive. So what's the right end behavior?
As x goes out, it's going to go up.
You're going to go up. Y is going to go up as we go way out to the right. Okay? Now we take x as a very large negative. What about x cubed? Very large negative or positive? Negative times a positive 5 results in still negative. So as we go, this is the left end behavior. The left end behavior means x, yep. And so will y be positive up like this or negative like this? Negative. Okay? We don't care about the middle right now. We're just looking at the ends. The ends. Questions on A? Does it make sense?
Why is x negative?
So if you think about, like, say, -2. If you multiply -2 together 3 times, well, you got a negative or a positive. You see? because if it's an odd number of times that you multiply a negative, it'll take you back to a negative. But if it's an even number, it'll be positive, right? Yeah. Yeah, good question. Okay, this one, leading term, 9x squared. And wrong. It's this one. And you got to notice that we're subtracting it. So all the details are important. Okay, so first start with a very, very large positive value. Very, very large positive value. Just start with x to the fourth. X to the fourth. Very large positive or negative? Positive. But then we're going to take that positive and multiply by -2. So we get y will become a very large negative. Okay, then this one is x, a very, very large negative number. Just do the x to the fourth first. So x is a very large negative. What about x to the fourth? Positive, because it's even number of times that we're multiplying together. So now we're back to positive, and we're going to multiply by negative. So we're going to also very large negative. Did I lose you? Does that make sense? So for this one, the end behavior would be, as we go way out, what's the right end behavior? Does y go up or down? Down. What's the left end behavior? Down. So the end behavior for this one will be like that. Okay, so this is a little trickier because we need the expanded form. And expanding this would take 5 or 10 minutes. We'd start off with like 16 terms or something, or maybe 20 terms that we'd have to put together. So we need a quick way just to get the leading term. That's all we care about. So how can we get the leading term? Well, all the terms are formed by just taking some combination of one thing from each. So we'll take the highest power thing from each. So what's the highest power we can take from x squared? X squared. So now we got x plus 3 quantity squared. What's the largest term we'll get from that? Another x squared. You see? If we multiplied that out, the biggest thing we'd get would be x squared. What's the biggest thing we get from this? 3x and x. So in all the different combinations of multiplying one from each, the biggest power of x will come when we pick the biggest powers of x from each. So what's that resulting leading term? 3x to the 6th. As x gets large positive, what does y do? So that's easy, right? X to the 6th will definitely be positive times positive number, so positive. As x becomes a very large negative, what about x to the 6th? Large positive. So that large negative becomes large positive as you multiply it together an even number of times. Take that positive, multiply by 3, we get large positive again. So the end behavior of this h is way out at the right, we go up. Way out at the left, we go, or y goes up. So there's the end behavior for that one. Way out to the right, y increases up. Way out to the left, y increases. So then we're still going to do the top hat. Don't pack up. But so on Monday, then we'll talk about middle behavior of the graph. So we got end behavior. You got some practice at that. And then Monday we'll talk about middle behavior, and then we'll put it all together. So we'll be able to recreate a sketch of these graphs by their end behavior and by what we call the middle behavior.
This will be included on our test.
Yes. So we have class on Monday when we come back and Wednesday when we come back. Then you have your exam Thursday. I'm going to get those materials up for you in the next day or two. So if you want to study over break. And then you have a written homework that's posted, which is due the day before the exam. And you can start on that as well.
Are we doing any web work for this one?
Oh yeah, when I put the review materials up,
Okay.
I'll put a web work up. Yep. Okay, I think you like the... Oh, I never... Hurry. What's today? 8th? No. Okay. That usually means it's done. Sorry. Here we go. Okay, so people got this wrong in the first class. 2 people got this wrong. So A is no, B is no, C is yes, and D is no. But people got it wrong in the first class. And we get 100% here. We can do it. So, the correct answer is C. Is everybody in? Okay, there's 100. Can I deactivate? Or maybe someone was just trying to be funny in the other class. Let's see. Visible. If I find out who you are, you're in trouble. Okay, have a great break. Be safe in your activities.
Here's mine. I don't know if you actually
Okay.
want it. And
All right.
then I just wanted to let you know
Oh, right. I got your email.
I actually
Sorry I
have,
didn't get back to you.
It's in my sphere, the little bone in your skull that looks like a butterfly.
Uh-huh.
So it's
Okay.
fabulous.
You better though?
Yeah, I just have to take
Okay.
I have a big problem.
A big problem? Hold on a sec.
Yeah.
Hold on a sec.